We're going to do some extensions of permutations and combinations, but where the objects we're dealing with are not necessarily distinct. In the previous several sections, we've been limiting our consideration to distinct objects, no two of them the same. We'll start this with permutations of indistinguishable objects, and here's a type of problem that this would involve. In how many distinguishable ways, that is, you can actually see the difference, can the letters A, B, B, C, C, C be arranged in a row? There are 5 A's there, 2 B's, and 4 C's, and we're going to have to live with that number of them, but how many different ways can we rearrange them? How many ways can we rearrange them? So here, we've already done this problem, but here's a restatement that shows us how we can do this already. This says, same thing, how many strings, ordered linear arrangements, of the letters A, B, C are there of length 11? How many have exactly 5 A's, as we have here, 2 B's, and 4 C's? Well, we know how to do this, like I said. Let's see how we can do this. So what we would do is, first of all, of the 11 slots, we're going to pick 5 spots of 11 for A's. So we're going to choose 5 of the slots 1 through 11. It's like picking 5 numbers from 1, 2, 3, etc. through 11. And it's not a matter of picking them in order. We're just picking the locations. This would be 11, choose 5. Now we'll pick 2 of the rest. How many are left? 6 for B. So that would be 6, choose 2, and then finally we have to pick 4 of the 4 left for the C. And that means we're 4, choose 4. So there it is. But let me rewrite that. We have done this once before, but if we rewrite that, what we'd have is 11 factorial over 5 factorial, 6 factorial, 6 factorial over 2 factorial, 4 factorial, 4 factorial over 4 factorial, 0 factorial. Remember, that's just 1. And some of these cancel, and this is always the way it works out. And so what we get in the end is 11 factorial divided by 5 factorial, 2 factorial, 4 factorial. That's a 4 right here. It doesn't really look like it, but that was a 4. So the 11 is split into 5, 2, and 4. Those numbers down the bottom before taking the factorial add to 11. And we're taking the 11 slots and splitting them into 5 of them for A, 2 of them for B, 4 of them for C. So the general statement, the general theorem that deals with this says the following: the number of different ways or distinguishable ways to arrange n things in order in a row if there are k different types. Now above we had 3, A, B, C, k different types of things, and there are n1 of type 1, n2 of type 2, etc. through nk of type k, so that those numbers n1 through nk add to the total of n, just like we had before. 5, 2, and 4 added to the total 11, like so. Then the number is the n factorial divided by the product of n1 factorial, n2 factorial through nk factorial. And the proof is very much the way we did it before. What we do first of all is pick we'll pick n1 spots of n for type 1. Type 1s are all the same. So that'd be n, choose n1 spots, and then we'd pick n2 spots for type 2, and that'd be, well, let's see, there's n minus n1 left, right? And we choose n2. And then we'd have, for 3, if we have 3 of these, it'd be n minus n1 minus n2, choose n3. So n3 spots type 3. Keep doing this, and at the end here we're going to pick NK spots for type K. And how many are left? Well, there's only NK left because we've chosen N minus N1 minus dot 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 NK minus 1, and we're going to choose NK. But because the number of, or the NKs, the NIs, all add to N, this is just NK on the top. And if we write that all out, this is N over N factorial over N1 factorial N minus N1 factorial. The next one starts with the N minus N1 factorial on the top, because that's how many are left. And then we have down here N2, and then the difference of these two guys right here is N minus N1 minus N2. And those are both factorial. And you can see that this will give us a great cancellation. I'm not going to write down a whole lot more, etc. How about that? Dot, dot, dot. In the end here we have N minus N1 minus dot, dot, dot minus NK minus 1 factorial divided by NK factorial. And then the difference here is just 0. This minus that is just 0 because the NI's add up to N. But the cancellation works just like it did before. And so this cancels with the previous one here that you don't see, and we do get indeed N factorial over N1 factorial, N2 factorial through NK factorial. So let's do, I think we have time to do one more example of this. So when testing a claim that someone has ESP, a researcher uses a deck of 20 cards that has 4 each with the symbol of a triangle, a square, a circle, a star, and a dot. So you've got these cards that look like this, but the person being tested doesn't see what's on the card, but they know there are 5 choices, and so you go through these and see how many of them they would get. So the question is, in how many distinguishable orders can the cards be arranged? Okay, and how many different ways can this be arranged so that the answers would differ at some point along the way? And it is just what we had before. We have these 5 groups. K would be 5, and each of the Ni's is equal to 4. There's 4 of each type, and so we're trying to figure out how many ways you can order these or arrange them distinguishably with those groups. So we can use either the original strategy of picking spots for each of them, or the expression we have above, which is 20 factorial divided by 4 factorial, 4 factorial, 4 factorial, 4 factorial, 4 factorial. Right? Okay, you could write that as 4 factorial to the 5th if you wanted to, but that's in fact the answer to this. So let's stop this one.